All right, I think we're ready to go. So we're going to briefly talk about the ratio test and we'll talk about a few other tests. But I just wanted to kind of point out the reason the ratio test works is because what we're doing is we're essentially seeing that. So for example, in this series, n squared over 3 to the n, we start adding up terms. At first, they're not looking very geometric, and they're not ever actually geometric. But when you go way out here, this 100th term and the 101st term, this term is essentially or very close to 1/3 times that term. And so once you get way out to the end, it starts really behaving geometrically. It's essentially just times 1/3, times 1/3, times 1/3. And if your ratio is between -1 and 1, we know we get convergence. So if we actually look at the ratio between the 101st and the 100th term, we see that after some simplification, it ends up being 0.3403333 forever, which is pretty close to 1/3. And you can see that if you went even further, you get even closer and closer to 1/3. So since that's the case, we can do the actual work of taking the limit of the n+1 term over the nth term and seeing that it actually is 1/3. If that ratio is 1/3, then the series does converge. So big picture, when you're using the ratio test, you're just saying, oh, essentially the series looks a lot like or acts a lot like a geometric series that either converges if r is between -1 and 1 or diverges otherwise. So kind of neat. Let's look at a couple other examples just to kind of see. So let's say, so actually what I should really say is, and I know I said this before, I'm gonna say it again, ratio test. When do I use the ratio test? If I see a factorial or something raised to the nth power. None of these things are 100% always going to work every time, but that's the usual idea. Is if you see one of those two things, that's probably going to mean ratio test is a good idea. So let's look at something like the sum from n equals 2 to infinity of n times natural log of n over 4 to the n. I will point out, I'm not thrilled about this one, right? It looks a little bit dicey, but I'm still going to try the ratio test because I have something raised to the nth power. So I have the limit. I should really write ratio. As n goes to infinity. Okay, here's my n+1 term. So n+1 times the natural log of n+1 over 4 to the n+1. And instead of dividing by n times natural log of n over 4 to the n, we're going to multiply by the reciprocal. 4 to the n over n times natural log of n. And then we're going to combine similar things. So I'm going to definitely rewrite this as the limit as n goes to infinity of n+1 over n. We know that's going to go to 1. And then natural log of n+1 over natural log of n, we'll have to deal with that in a second. Oops, sorry, natural log of n. And then finally, 4 to the n over 4 to the n+1. Technically, if I want to be precise here, I should probably break this up into the product of 3 limits, which is kind of annoying. But specifically to deal with this natural log part, I kind of need to do that. So I'm going to write this as the limit as n goes to infinity. Actually, I'm only going to write it as 2 limits. n+1 over n times the limit as n goes to infinity of the natural log of n+1 over the natural log of n times 4 to the n over 4 to the n+1 is just 1/4. So I could even put that on front, I suppose, would maybe make the most sense. So clearly that's going to be 1. And to do this part here, I'd have to use L'Hopital's rule. This is going to be equaling 1/4 times 1. And then using L'Hopital's rule, the limit as n goes to infinity of the natural log of n+1 is 1 over n+1. The natural log of n is 1 over n. And then that limit's also going to be 1 because we can bring the n up top. So you end up getting 1/4 times 1 times 1, which is 1/4. I should point out, because it is worth mentioning, you can only do this thing where you break up a limit of a product as the product of the limits if all of the limits exist. If you end up getting one of these being infinity or some other sort of divergent sort of thing, you couldn't say necessarily the whole thing diverged because maybe you had some weird, oh my gosh, indeterminate form that you actually were able to deal with in a different way. So this totally works if all the limits exist and they're nice real numbers, but if one of them doesn't, then you kind of have to say, I should probably go look at something else. Let's look at another example just to kind of see if I have the sum from n equals 1 to infinity of n cubed over, sure, n 2n cubed plus 2n minus 6. And here I definitely should not use the ratio test. I could use the ratio test. It's not going to get me anything good. I will point out, if you do the limit as n goes to infinity of your an plus 1 term over an, you're going to get 1. I don't really want to write it down because it's just a lot of writing, but I think you should definitely do the work to see, oh, that's 1. So that test is inconclusive. What we should have done is seeing that we have a rational function, which almost always is going to be doable using the, what I really should have done instead of, so I will say, you can show this diverges by doing a limit comparison. What I really should have done was seeing that the degree on top and the degree on the bottom are already the same, which means the nth term test is going to show me divergence, because the limit as n goes to infinity of n cubed over 2n cubed plus 2n minus 6, 1/2. Now be careful. This is where people start getting their tests confused. You might be like, oh, my limit's less than 1, it converges. No, right? We use the test for divergence here. And when you're using the test for divergence, we're saying, oh yeah, the sequence converges to not 0, so the series diverges. But it can be a little bit confusing because there's a lot of tests that we take limits, and depending on what the limit you're taking of matters what your value is, right? If it here, getting not 0 is meaning divergence, but right, for the ratio test, less than 1 means convergence, greater than 1 means divergence. Oh yeah, here's a good one. Yeah. Here's a couple classics. Sure. So we want to find the sum, n equals 1 to infinity of n factorial over n to the n. This is one of my favorite questions to ask on a test. If we use the ratio test, it is going to come out to be convergent. We just have to be careful. At least I think it's going to, I believe it's going to be convergent. I'm pretty sure. Let's see. But it's definitely a ratio test kind of question, because we see the hallmarks, right? We see a factorial and an n power. So I'm going to do the limit as n goes to infinity of n plus 1 factorial over n plus 1 to the n plus 1 times n to the n over n factorial. And now we definitely need to do some simplifying. So I'm going to rewrite this as the sum from n equals, I'm sorry, not the sum, apologies. The limit as n goes to infinity. The n plus 1 factorial over the n factorial, we definitely want to get comfortable with saying that's just n plus 1. I'm going to write it down one step just to show the work. But yeah, let's go ahead and just remind ourselves, yeah, that whole thing just going to be n plus 1. And then n to the n over n plus 1 to the n plus 1, I'm going to do one thing. I would love for those to have the same power, because then I can kind of group them together. So right, this is n to the n over n plus 1 times n plus 1 to the n. It's a pretty standard thing to do. And then actually this works out really nicely, because then you have the limit as n goes to infinity of n plus 1 over that n plus 1. And then over here you have n to the n over n plus 1 to the n, which I'm going to write as n over n plus 1 to the n. Those cancel. And now you're left with the limit n goes to infinity, n over n plus 1 to the n. And I feel like this takes a little bit of seeing. So this one is extra tricky. You kind of have to do a thing where it's kind of one of those problems where if you never knew how to do it, you never would know how to do it. Someone has to have shown you kind of one time, and then you're like, oh yeah, I know the trick now. So here the trick is to actually rewrite this as its reciprocal. So I'm going to write this as, instead of n to the n over n plus 1 to the n, I'm going to write it as 1 over, sorry, don't forget the limit, n plus 1 over n to the n. Now, first of all, let's all agree that's true, right? If you flip a fraction, you can put it in the denominator, it's the same thing. But now check this out. This is really the limit as n goes to infinity of 1 over, well, n plus 1 over n divided by n is 1, and 1 divided by n is 1 divided by n. And now the idea is that this should look familiar. That is definitely E. The limit as n goes to infinity of 1 plus 1 over n to the n is E. So you get 1 over E less than 1. So this diverges, or it's converges, sorry, converges. So this converges by the ratio test. I will point out that if you take, so a nice thing to know, this is true, is if a series converges by the ratio test, the reciprocal series is going to diverge and we'll have the reciprocal limit. So I will just also mention here as a bonus, the sum from n equals 1 to infinity of n to the n over n factorial is going to diverge by the ratio test. I think it's worth you doing it on your own, but it is true that the limit as n goes to infinity of the an plus 1 over the an term is going to be, instead of 1 over e, it's going to be the reciprocal, which is just e, which is greater than that. And that's always, right, that's something nice to just know. If ever you have a series that's the reciprocal of another series, and the ratio test worked, the ratio test will work again, but it'll give you the opposite conclusion because you'll have the reciprocal value. So the ratio test is nice. It does what it does. You can apply it and should apply it when you have things with factorials and things raised to the nth power. I will say we have another test that is similar to the ratio test. Oh, and I think there's a homework question for Casals that is, as far as I know, a hard question to answer, but I do know the answer to it. But let's look at something like this for a second. So let's say we have the sum from n equals 1 to infinity. What have I got here? Yeah, n plus 1 over 2n plus 3, all raised to the nth power. And what I will point out is if we start writing out terms, we're again going to get this kind of idea where it's going to start behaving geometrically, right? If you go away, your first term is 2 over 5, and then your second term is 3 over 4 plus 7 is 4 plus 3 is 7 squared, and so on and so on and so on. When you get up to the 100th term, your 100th term is like 101 over 203 to the 100th power, and your next term is 102 over 205 to the 101st power. But both of these numbers inside the parentheses are getting very, very close to 1/2. And so what we can see is essentially this next term is just a multiple of 1/2 compared to the previous term, because the power is 1 higher, but the ratio inside the parentheses is essentially the same. Could you use the ratio test here? Totally. Ratio test definitely applicable. But specifically, when you have everything raised to the n power or the 2n power or the something times n power, instead of the ratio test, it's easier to use the root test. So the root test essentially says the same thing as the ratio test. So we apply the root test, which I will do first and then write down second. The root test just says if you take the limit as n goes to infinity of the nth root of whatever your sequence is, in this case, n plus 1 over 2n plus 3 to the nth power. Well, raising something to the nth and then to the 1 over n, those just end up canceling each other out, and you get the limit as n goes to infinity of n plus 1 over 2n plus 3, which is just 1/2, and that's less than 1. So again, the root test also shows you what sort of ratio your sequence is approaching. So more generally, I should write down, so this series from n equals 1 to infinity, n plus 1 over 2n plus 3 to the nth power converges by the root test. The root test and the ratio test are very, very similar. I would encourage you to link them together in your mind. You use the ratio test when you have something that looks kind of funky with a factorial or something raised to the nth power. And then specifically, if you have something all raised to the nth power or the 2n power, or a place where it's going to be really easy for that being raised to the 1 over n to cancel out your power, that's when you want to use the root test instead. Here is the root test. It's pretty much the same as the ratio test in that you're going to say, we're going to take the limit as n goes to infinity of the nth root of the absolute value of your sequence A sub n. If that limit is equal to some ratio R, this is going to, then the series from n equals whatever to infinity of A sub n converges if that ratio is less than 1, diverges if that ratio is greater than 1. And as is typical, inconclusive if that ratio is equal to 1. Interesting thing to know here, and this I believe for Casals there is a homework question that asks about this. The root test is actually a stronger test than the ratio test. And when I say that, I mean that there are series that you can show converge using the root test, but you cannot show converge using the ratio test. But the opposite is not true. Any series that you can show converges by the ratio test, you could, in theory, also show as convergent by the root test, which is kind of interesting. And yeah, I think there's a question on Casal's homework about that. I really am not sure how he expects to show that, but that is the thing that I know to be true, that the root test is a stronger test than the ratio test. And then we can look at some examples. I guess I could start. I know I was numbering things and I kind of lost my. To me, the root test never feels particularly useful. For example, if I have, like the sum from n equals 1 to infinity of say n plus 1 over 3 to the nth power, yeah, I can use the root test here. It just always, to me, the root test examples always feel very contrived. It's like, oh yeah, everything raised to the nth power. Of course, I'm going to use the root test. That doesn't mean it doesn't come up. The limit n goes to infinity of, usually instead of writing the nth root, I like to just jump straight to writing everything raised to the 1 over n power. I don't write the absolute values if everything's already positive, but here we're just going to get the limit then goes to infinity of n plus 1 over 3, which is infinity, so we get divergence because that is definitely bigger than 1. We also probably could have just seen that by using the nth term test, right? Our sequence here is not getting closer and closer to 0. It is definitely getting infinitely large. So again, not a very, I think, interesting example, but it is an example. Let's look at, oh yeah, here's a better example. Let's say we have the sum n equals 3 to infinity of n to the 2n over 2 to the n squared. And this is probably an example where the root test is actually better specifically than the ratio test. Because while you maybe do the ratio test, it's going to get messy, right? You're going to have n plus 1 to the 2 times n plus 1 over 2 to the n plus 1 squared times the, right? It looks terrible. So let's try the root test. So limit n goes to infinity of all of this stuff nth root. So n to the 2n over 2 to the n squared. Be careful, just as a quick reminder, 2 to the n squared is not 2 to the n squared. When you have powers to powers and there are no parentheses written, the default, the thing that we're supposed to say is that 2 to the n squared is 2 raised to the power of n squared, like that in parentheses. So it can be a little confusing because it seems like they should be the same, but they're definitely not. The one I always keep in mind is that 3 to the 3 to the 3 is not equal to 3 to the 3 to the 3. This first one is 3 to the 27th power. The second one is 3 to the 9th power. So just be a little careful when you have powers to powers can be a little bit dicey. So let's see what we've got here. If I start rewriting this, the limit as n goes to infinity of n to the 2n to the 1 over n power over 2 to the n squared, the 1 over n power. But now we can say, well, you got something raised to a power like that, you can multiply those powers. So this is going to be the limit as n goes to infinity of n squared, because 2n times 1 over n is just 2. And on the bottom, we're going to have, well, n squared times 1 over n is just n. And we've seen in the past this is definitely why we've talked about this, the exponentials are always going to overpower polynomials. So this, I mean, you could also, okay, you could use L'Hopital's rule twice, but we know this limit's going to be 0, it's less than 1. So this series converges. So again, root and ratio test, I feel like, are kind of the easier tests to apply because you don't have to know anything really. All you have to know is, I mean, you have to know how to do the test, but unlike the comparison tests, you don't have to think about whether you know this thing converges or diverges and come up with something to compare it against that does the behavior. So root test and ratio test, very easy to apply, and just try them out. Again, you're looking for something raised to the nth power or an n factorial. That is usually when you're thinking root or ratio test is a good idea. Okay. Other tests. Alternating series test. Or as my good friend wrote, and I think it's the idea, the alternating series convergence test. So much like the nth term test, also called the test for divergence, only can show you that the series diverges or the test is inconclusive. The alternating series convergence test can really only show you a series converges. It can also technically show a series diverges, but really what you're going to, well, I'll get, when we get there, we'll get there. So let's look at the most famous example, the alternating harmonic series. Which is just the sum from n equals 1 to infinity of -1 to the n plus 1 over n. Or as some people often prefer to write, they like to write the alternating part kind of factored out in front. I don't. I feel like it takes up more room. But they write like this because then the non-alternating part is more obviously just the 1 over n. This is 1 minus 1/2 plus 1/3 minus 1/4. And so on and so on and so on. So does this converge? Well, as long as the alternating series meets 3 specific conditions, the answer is yes. So here's the idea I really keep in mind. If I'm going to look at the sequence of partial sums just for a second, but I'm actually not going to write them down. I'm going to graph them instead. So yeah, let's do it this way. Oh yeah, I don't love doing it like that. Do it like this. So I'm just going to start putting my partial sums here. So let's say here's 1. And so here's what S1 is equal to. Right? S1 is equal to 1. S2 is 1 minus 1/2. So I'm going to subtract 1/2. I'm going to go, okay. So here I should write, so here's S2 equal to 1 minus 1/2. And I will point out, to get from there to there, we just subtracted off A sub 2. Right? So first, we did A sub 1, and we subtracted off A sub 2. And now, to get S3, we're going to add on a third. So I'm going to go, which is not quite as much as a half, maybe it's like that much. And I'm going to end up over here. There's S3. Whatever 1 minus half plus a third is. And I think you might start to see what's happening here. I'm going to keep subtracting and then adding and then subtracting and then adding. And every time I do that, I'm going to add or subtract a smaller thing. So, right, I subtract a 4, add a 5, and I just keep essentially zeroing in on whatever this partial sum has to be. It's kind of cool, I think. So yeah, that's the idea, is that since the terms of the sequence, I should say since the, well, yeah, the terms of the sequence are decreasing, I should say since the non-alternating terms, right, that's what we typically look like, are 1 decreasing and 2 getting closer to 0. That's all we need. I used to think that those meant the same thing when I was a student. Like, oh, if it's decreasing, or I mean, basically say like, if the limit was 0, then it's decreasing. And I was like, well, that, but that's not technically always true. You can come up with sequences whose limit is equal to 0 that aren't always decreasing. They can kind of like do like a decreasing and then get bigger, and then like you can kind of do that. And so you have to really check both. So here is what so I should say, first of all, this series does converge. This alternating series, sum from n equals 1 to infinity of -1 to the n plus 1 over n converges. I'm trying to think if there's anything else I want to say about this before I say it. I feel like there was something there. No, that's all right. Okay, cool. Yeah. So here is the actual alternating series test. The alternating series. And I do like putting in the word convergence test there because it reminds me that it really only ever shows me convergence. So this series, the sum from wherever to infinity of -1 to the n times a sub n. And when we write it like this, we typically think of essentially the a sub n's as the non-alternating parts. So in the previous example, the a sub n would just be the 1 over n, 1 plus 1/2 plus 1/3 plus 1/4. So this is going to converge if and only if the following 3 conditions are met. Condition 1, the a sub n's are positive. That's typically kind of given, but it is something you have to at least think about for a second. And then thing 2, the other things I said, that the limit of the a sub n's are 0, which makes sense because if they weren't 0, you could say that the series diverged by the nth term test. So that's typically, oftentimes students will, or people in general, not just students, will do the alternating series test and we'll get to this part and it won't be 0. And they're like, oh, the alternating series test fails, it diverges. But really what you should say, if this part doesn't equal 0, is that, oh, the limit of the sequence isn't 0, so the series diverges by the nth term test. I should point out, the limit of the series typically doesn't exist. Because if it's not 0, it's bouncing back and forth between numbers that aren't getting closer and closer to the same thing. And then thirdly, and this is always the one that's kind of a pain in the butt, we have to show that the sequence is decreasing, but the next term is less than the previous term. So that's how we show a series converges by the alternating series test. And like the name would imply, series has to be alternating for this to work. You can't apply it to a non-alternating series because it's not going to fly. Yeah, right. For example, right, we know that the regular harmonic series meets all these conditions aside from being alternating, and it definitely diverges. So cannot be applied to a non-alternating series. Let's look at another example. Say we want, I'm like trying to keep the numbering, but the numbering has gone away. Let's just do a new numbers. We're new section. So the sum from n equals 1 to infinity of -1 to the n plus 1 times 1 over the cube root of n. I should mention, it doesn't matter if your series starts with a positive or negative term, right? It could have been 1 minus a half plus a third, etc., or -1 plus a half minus a third. It does matter that every other term changes sign. That's what alternating really means. So let's check. 1, a sub n equal to just the non-alternating part is definitely positive for n bigger than or equal to 1, which is where we're starting at. Thing 2, yeah, the limit's going to be 0. The limit as n goes to infinity of 1 over the cube root of n definitely is 0. And here, showing it's decreasing, I don't think is very hard at all. So to show the decreasing part, all we're going to do is say that, okay, well, 1 over the cube root of n plus 1 is less than 1 over the cube root of n. I don't think you have to write anything else here because I think it is pretty obvious that, oh, here my denominator is a little bit bigger. That thing is definitely going to always be smaller. That checks out right away. I think we can say right off the bat, okay, great. So my series from n equals 1 to infinity of -1 to the n times 1 over the cube root of n definitely converges by the alternating series test. Yeah, it's one of my favorites. Okay, let's do one more. The next, or at least one more. The next one is kind of a terrible pain. Well, it can be depending on how you approach it. But let's look at the second one here. The sum from n equals 2 to infinity of -1 to the n times the natural log of n over n. Typically, the other two things, aside from showing it's decreasing, are pretty straightforward, right? Thing one, thing one, technically, natural log of n over n is not positive for every n I pick. Because if you plug in 2, oh yeah, it is. Sorry, I'm thinking about plugging in 1. Yeah, we're good to go. This is bigger than or equal to 0 for n greater than or equal to 1. And we're certainly starting at n equal to 2, so we're good to go. Natural log of 1 is 0. Natural log of like 1/2 would be negative. But natural log of 2 is just less than 1. And then showing the limit 0 is usually a straightforward yes or no, right? We can take most limits not too terribly. And if we do that, we're going to get the limit as n goes to infinity using L'Hopital's rule, 1 over n over 1, which is certainly 0. It's usually the third thing. It's kind of a pain. So one option, which is usually not the option you want to use, is to show that an plus 1 is less than an by showing that the natural log of n plus 1 over n plus 1 is less than the natural log of n over n. And this is not a cakewalk. Doing this is actually relatively challenging. It can be done. I'm happy to show you all how to do it if you would like to see it. But I will tell you, unless your sequence has a factorial in it, usually the way we're going to show that the sequence is decreasing is by showing that the derivative of the function is negative where it matters. So instead, what we're going to do is show that f of x equal to the natural log of x over x is decreasing where it matters for x greater than or equal to 2. Or at least somewhere. So let's see. So I can take some derivatives. My derivative here is going to be f prime of x is the bottom times the derivative of the top minus the top times the derivative of the bottom, which is 1 all over the bottom squared. And if I simplify this, that's going to be 1 minus the natural log of x over x squared. The nice thing about doing this, I think, is it's almost always going to be a quotient rule because you're almost always looking at, right? Most series we deal with have like something on top, something on the bottom. And then when you use the quotient rule, the bottom always ends up being squared. So it doesn't matter what this is, that's not going to change the sign of this whole thing. If I want to show that the function is decreasing, actually the derivative is negative. So if I want this to be negative, what I really need is the numerator to be negative, which means that x has to be bigger than e, because I have 1 less than the natural log of x, and if I e both sides, I've got e to the 1 less than x. So x has to be bigger than e. So great. So here's what I'll say. Technically, we're starting at 2. That means we aren't actually getting it, right? Because we have x has to be bigger than e. But it doesn't matter. It doesn't matter that your first 5 terms aren't doing what you want. Or your first 1,000 terms aren't doing what you want. As long as eventually you get to the place where these things are true, that is actually what matters. So what we can really say here is, yeah, this series converges. Because certainly the natural log of n over n is always positive, and the limit as n goes to infinity of natural log of n over n is 0. And lastly, that the series is decreasing for n greater than e, which is fine, even though we didn't technically start there. Yeah, later, if you're curious, come to office hours sometime, and I'll definitely talk about the longer way of showing that this is decreasing, but I don't think you really want to do it that way. Let's look at one more example. We got time. Sure. So let's say we have actually two more examples. So here's an example, n equals 1 to infinity of -1 to the n plus 1 times 2n plus 3 over n plus 1. I almost always kind of ignore the first thing. Like yeah. Are those all positive? Definitely, when n is bigger than or equal to 1. So I typically move on to the second thing right away. Say, okay, well, what's the limit? I do think it's always worth checking the limit to infinity before you check to see if it's decreasing, for two reasons. One, checking it's decreasing is harder. Two, you don't have to check it if the limit's not 0. So if the limit isn't 0, you would have spent time doing work you didn't really need to do. So if I take the limit here, n goes to infinity of 2n plus 3 over n plus 1, that's going to equal 2, not 0. So then we can say that this series diverges by the test for divergence. Diverges by the nth term test, or test for divergence. Because the limit of the actual sequence of -1 to the n plus 1 times 2n plus 3 over n plus 1 does not exist. It's bouncing back and forth between +2 and -2. And that limit does not exist. It certainly doesn't equal 0. So I usually don't actually care about the non-existing part. I just specifically care, hey, that's not 0. So the series diverges. In a similar way, I'll just point out that the sum from n equals 1 to infinity of sine of n diverges by the nth term test as well. The reason that actually I'm mentioning this series is because I just want to point out this series is not alternating. You have some sign changes, but it's definitely not a back and forth sort of situation. So this, I just want to say, is this is not an alternating series. I think like sine of 1, sine of 2, sine of 3 are all positive, but then sine of 4, sine of 5, sine of 6 are all negative. It's weird, right? Because sine's as a function where it's positive in between when your inputs are between 0 and pi, and it's negative when your inputs are between pi and 2 pi, and then you can keep going around. So it's very kind of strange. But the last one I wanted to point out was, well, I should never say the last one. There's never a last one until I'm out of time. The next one I wanted to point out is the sum from 1 to infinity of -1 to the n plus 1 times n over n cubed plus 1. And you could totally show this converges by the alternating series test. It is certainly plausible to show that, well, certainly thing 1, n over n cubed plus 1 is positive. Thing 2, the limit as n goes to infinity of n over n cubed plus 1 is certainly 0. And thing 3, it is decreasing. Let's go ahead and do it just because it's worthwhile. I am going to, so if I have n's on top and n's at the bottom, usually trying to show it like the straightforward an plus 1 less than an way is not always easy. Usually taking the derivative is pretty straightforward. So let's try that. So let's see. So I like to write it in terms of x just because, I don't know, that's the way I was taught to do it. You can do it in terms of n though if you want. My f prime of x is going to be bottom. I said x, but I started writing n's. Sorry about that. bottom times the derivative of the top minus the top. Right, bottom derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And if we simplify this, that's going to equal x cubed plus 1 minus 3x cubed over, it doesn't really matter what the bottom is, x cubed plus 1 squared. Simplifying the top, we've got 1 minus 2x cubed over x cubed plus 1 squared. And that's definitely going to be negative for x larger than or equal to 1, which is where we're starting. I mean, really for smaller values of x, but I'm just going to start where I'm starting. So this is definitely less than 0 if x is greater than or equal to 1. And if the derivative is negative, that means the function is decreasing. So great, we showed all the things. But we could have done less work. Because what we could have said is, instead of doing this, we could have used another test, which is the absolute convergence test. So the absolute convergence test basically just says, if the series of the absolute value of your sequence converges, then so does your original series. I don't want to call, oh no, yeah, sorry. So that's basically it. If the sum of the absolute value of an converges, then so does the sum of an. This is not true for divergence, right? And let me just, so actually, let me point that out. Not true for divergence. Any alternating P series that would have diverged is an example of this. For example, the sum from n equals 1 to infinity of -1 to the n plus 1 over n converges. But the absolute value, so, or I should say the sum of the absolute value of -1 to the n plus 1 over n. This comes up a lot. When you take the absolute value of -1 to a power, it just becomes 1. Because -1 to any power is just -1 or 1, or -1 or 1. And the absolute value of either of those is just 1. This really just becomes the sum from n equals 1 to infinity of 1 over n, which is divergent. So what I'll point out, just because this come up, is this series here, the one that's convergent, is called conditionally convergent. And specifically what we mean by that, a series is conditionally convergent if it's an alternating convergent series whose absolute value diverges. Or in other words, is not absolutely convergent. Let's go back to this example though, which you can still see. So we could have said, oh, this series, -1 to the n plus 1 times n over n cubed plus 1, n equals 1 to infinity. Let's test for absolute convergence. So does this series from n equals 1 to infinity of the absolute value of -1 to the n plus 1 times n over n cubed plus 1 converge? Well, if we simplify it, we're just getting the sum from n equals 1 to infinity of n over n cubed plus 1. Does that converge? Or how could we show it converges or diverges? So the nth term test could show only what? Right. But if you take the limit of this part, what are you going to get? It's going to go to 0, which means that the nth term test doesn't show anything. So what I would think about using here is either the comparison test or the limit comparison test. So if we just use the direct comparison test, this is going to converge by direct comparison with the sum from n equals 1 to infinity of just n over n cubed, which is the sum from n equals 1 to infinity of 1 over n squared. So it feels kind of like a lot to say here, but what we're saying is this, so this series, the absolute value series, converges by comparison with this convergent series. And then we can say that means this series converges because this series is absolutely convergent. Kind of a lot to say. Let me write down one thing here. Yes. So, right. So this converges by direct comparison. So therefore, our original series from n equals 1 to infinity of -1 to the n plus 1 times n over n cubed plus 1 is convergent by the absolute convergence test. Now, really, the words we actually like to say is series is absolutely convergent. Now, I'll point out, if we had done the absolute convergence test and we hadn't gotten convergence, that doesn't mean the series diverges, right? It could still conditionally converge. So if you try to show absolute convergence and it doesn't work out, that doesn't mean you're done. It means you have to go back, and then you actually do probably have to go try and use the alternating series test. And again, just as an example, back from like the first things we were, or not the first things, but like the first examples we had here. If I had, where'd you go? Like, for example, if we had tried to use the absolute convergence test here, we would have gotten divergence. Because if we took the absolute value of that, we just have 1 over n to the 1/3, which diverges the p series. That doesn't mean we can say that this series diverges. We have to say, oh, well, it didn't converge absolutely. Now we have to go check to see if the alternating series converges by the alternating series test. But sometimes you have series that are not alternating, but are not always positive. For example, the sum from n equals 1 to infinity of, let me think here, which one I want to do here. Sure, let's do cosine of n over n squared. Cosine of n is certainly not alternating, but it is something that changes signs eventually. Like it's positive and a negative and a negative and a negative and positive, right? It's kind of, it's all over the place. Right? If you think about the graph of cosine, and think about how like you probably did 1, 2, 3, 4, 5, 6, how it would just be, you'd have positives and negatives. But you can totally use the absolute convergence test. So absolute convergence test. So we're going to look at the sum from n equals 1 to infinity of the absolute value of cosine of n over n squared, which I would not necessarily write the absolute value around the n squared because I know that n squared is already positive. And now, oh, we're out of time, but here's I'll say cosine, and I think I've said this before, cosine and sine are always between -1 and 1. So the absolute value of cosine is always positive and is always less than or equal to 1. So this series is definitely less than or equal to the series from n equals 1 to infinity of 1 over n squared. So we can say, oh, great, this thing must converge by direct comparison. Which means our actual series is absolutely convergent. So the sum from n equals 1 to infinity of cosine of n over n squared is absolutely convergent. Which means it converges. So when you say something is absolutely convergent, you're saying more than just that it converges, but one of the things you are saying is that the original series itself, without being altered, does converge. It's just we usually like to say all this because it says more. All right, I should stop there because we're 10:51.